Okay, so how do we decide when it's time for the run to stop? Why don't you edit your main input file and try, you can either set the maximum number of iterations you want to run for, or you can set the maximum time in minutes. And whichever one is lowest will win. So try setting 5 time steps as the max iterations and set the maximum time in minutes to be 30. This is in the temporal controls name list. Okay. And max time minutes may not be there. You may have to add it.
Is order important in this?
No. Order within the name list is not important. Order of the name lists is important.
We define the boss?
Oh, yeah, no, please define them both.
Boss.
Yeah, so try the first example where we do 5 time steps in 30 minutes. But then try the next example where we do 5,000 time steps and 1 minute. And you should see the first one will run normally and the second one will terminate after about a minute passes. And you can make that 0.5 minutes if you don't want to wait that long. So this is useful because on some machines, for Mira, for instance, you can chain jobs together. But the code needs to exit cleanly for the next job to start. And so if you know your wall time is 24 hours, and so you set this for 1,400 minutes, you'll stop just a little after 23 hours. And the code will exit cleanly when it does so. And then if you want, there is a command you can pass on the command line to Rayleigh, which is in-iter, which will override max iterations in the file. It'll just tell it run for two iterations in this example. If I say iterations, I mean time steps. I don't mean a iterative matrix solve. So then if you look in your temporal controls name list, there's some other things here that govern what sort of time step Rayleigh takes. Okay. And so there's a min time step, and if the time step becomes that small for whatever reason, okay, the code will stop. It will exit cleanly, but it'll stop. So you set this to something really tiny. If I were running even like a Boosanesque sort of non-dimensional simulation, 10 to the 13 is probably a pretty small time step. So set this to something small because occasionally the time step will just keep becoming smaller and smaller and your code will just waste a lot of time. So this makes sure it stops. And then there's a max time step that you can specify. Okay? And so you can say, I don't care what the CFL condition tells me, never take a time step larger than this.
Okay. Nick,
yeah.
So when I did the, limited it by minutes, I got iterations per second 163, which makes no sense. It was like,
yeah, I got that too.
Yeah.
Oh, you know what? Do you know what it does? I just remember this. The way it exits that loop is it changes the current iteration to the last iteration. So it probably, what did we have? I'll fix that. Thank you. It basically said, oh, I ran 5,000 time steps.
I see. Right.
That's a useful thing. Thank you. That's okay. So anyway, that's the min and the max time step. And then there's a CFL condition in the code based off of your flow speed, based off of the alphane speed if you've got magnetism on. And the idea is that whatever limit that gives you, you won't take a time step larger than CFL max times that. Okay, so this is just a standard CFL safety factor, is what CFL max is. And so the code has adaptive time stepping, so if the time step gets pushed down very far, it will try to bring the time step back up. But recomputing the implicit matrices for the time stepping is expensive, so you don't want to do that too often. So the min says, okay, if my time step has gotten down somehow below 40% of the CFL limit in this case, then I will readjust the time step size and recompute these matrices. Otherwise, it doesn't do that. Okay, and so you can play with those limits yourself. This is usually what I run with. If you didn't have the min there, or if you had the min very much closer to the max, the time step will jump around quite a bit because the code will try to raise the time step back up. So this is usually what I run with. Okay, so you can try something here. We can kind of experiment with this. Okay. So first of all, set your grid to what I've got up here, and then what you can do is you can give it a very large maximum time step, something that's much larger than the CFL limit, and you can watch it adjust the time step. And if you just run for 10 iterations, you should see this work. And then similarly, you can basically force a crash by giving it a minimum time step that's fairly large, and so when the code hits that, naturally it will crash. Okay? And just see how this functions. Okay, great. So the last portion of this module will cover checkpointing. Okay, and we've actually been generating checkpoints while we've been running every time the run completed successfully. So if you just in your module 2 directory, if you do an ls on the checkpoints directory, you should see something. So I guess the first question is, does anybody not see something there? If the code ran and finished, it should have at least saved one checkpoint. So what's there is basically everything needed to resume a run from the indicated time step. Okay, so you'll see files with this sort of structure. There's a lot more. You'll see some with Z, some with S, but the idea is that every time Rayleigh dumps a checkpoint, and we'll talk about when that happens and how to control it, it dumps a file with the grid. It dumps the fields, and we use a stream function decomposition. I meant to mention that earlier, and I did not. So there's a poloidal and a toroidal stream function, and that's actually what's used in the code to evolve the system. So those are called W and Z. Those are dumped, as are the pressure and the entropy or temperature field, and then the things needed to get the Adams-Bashforth method running again from that time step are also dumped, and that's why there's an A-B set of outputs. There's also a checkpoint log, which just lists every checkpoint that's ever been written in that directory, unless you deleted the log at some point, at which point Rayleigh will create another one. And then there is a little file called last checkpoint, which is really just for Rayleigh's use so that it can restart from the last checkpoint. We're going to talk about the fine-grained control of checkpointing here. Try resetting. You know, we were playing around with time stepping and trying to induce a time step crash. So reset your max time step and your min time step. Change the checkpoint interval to 2. But then before you do anything else, go in and clean everything out in your checkpoints directory. Okay? And then run the code for 10 time steps. Now I'm actually going to do that too so that I can do an ls here. Okay, so once you do that, if you look in your checkpoint directory, you should see something like this. So what it's doing, we've changed the checkpoint interval to 2, and then we ran for 10 time steps, and so it's dumped a checkpoint every other time step, okay, all the way out to time step 10. Okay. And so let's clear out the directory contents again, okay, and let's make a small modification to this exercise, okay. So let's change the checkpoint interval to 3. Okay, and we'll run for 10 time steps. Just pull this back up for a minute. Okay. what you should notice is that now we've dumped checkpoints every third time step, but there's also a checkpoint dumped on the 10th time step. Okay, and the reason for that is that by default, Rayleigh will not just checkpoint when you ask it to, but it will also save a checkpoint on the last time step. Okay, so if the run finishes normally, maybe the wall time ended on a weird numbered time step, Rayleigh will save that. If you want to not save it, you just add this little flag to your temporal controls name list. Okay, and if you want, you can try this. I don't know. There's a lot of value right now, but put that in there as false, rerun it, and you'll see that you didn't save time step 10, provided you clear out your checkpoints directory before that. So that's a feature in Rayleigh, but some people may not like it, so you can turn that off. Okay. But the basic idea is that checkpoint interval is what controls how often we checkpoint, and that's in time steps. So there's kind of another layer to the checkpoint in Rayleigh, which is what's fairly important. So checkpoints take up a lot of space. Okay, you're basically doing full 3D dumps of multiple variables. If you're doing a big run, that can take up a lot of space because you also usually want to checkpoint frequently so that you don't lose your work if something crashes. Okay. So what we use in Rayleigh are what I call quick saves. And these are basically rotating checkpoint slots. Okay, so you might have 3, 4, 5 slots, and on with a very high cadence, you're writing checkpoints to these slots over and over and over and over. So let's try implementing this quick save functionality here. So first, clear out your checkpoints directory so that we can actually see what's happened. And then set up your temporal controls name list so that you have a checkpoint interval of 5, but then we're also going to set these other two flags, the quick save interval, we'll set that to 2, and then we'll set num quick saves to 3. Okay. So num quick saves tells us how many slots we're going to have that we're just going to rotate in and out of, and quick save interval tells us how often in time steps we want to write one of these quick saves. I'll give everyone a minute, and then once you do that, run your code for 10 time steps, I should say. I'll do that too, actually. Okay, so if you've done that and you look in your checkpoints directory, you should see a different combination of files now. Okay. So we set our checkpoint interval to 5, and so that corresponds to these numbered dumps in the file names. Okay, so we've got one at 5 and one at 10. 10 was also the last time step, so that would have happened even if we'd run for like 11, or so we would have seen one at 11. Okay, and then we see all these little quick save files. Okay, so the quick saves are just numbered by the save slot. The file name there doesn't have the time step information attached to it. Okay, so the way to find that information is to look at the checkpoint log. Okay, so if you just do more on checkpoint log in that directory, well, yours will go out to 10, not to 14. I must have meant for you to run it for 14 time steps, but that's okay. All right, so if you look at the checkpoint log, you'll see a list of numbers, and then some of those have a second number beside them. So the standard checkpoints are just one number, and they're not indented. So that's just telling you when those were written. And then the quick saves are indented slightly and they have the quick save slot next to them. And so the way to read this is that we wrote a standard checkpoint at time step 5 and time step 10. And then on time step 2, we wrote to quick save 1. But then later at time step 8, we wrote to quick save 1. Because at 4, we wrote to quick save 2. And at 6, we wrote to quick save 3. And then on time step 8, we overwrote quick save 1. So the quick saves, they're really, like I said, they're mostly there just to make sure you don't lose your work. So if you want to see what's in them, you have to do a little bit of extra work and look at the log file here. And then I had some other examples. In this example, for instance, quick save 2 contained 4, and then it would contain 10. But this is kind of important. The standard checkpointing will always override the quick save. So if they come at the same time step, the standard checkpoint is written. Okay. So then quick save 2 was filled in on time step 12 in this example.